Good morning. I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the course titled Atomic and Molecular Spectroscopy. Today we are going to discuss quantum states and spectroscopic terms. Quantum states. In general, when an atom is present inside a material substance, it has central nucleus in which electrons revolve around circular orbits according to the Bohr's theory. But according to Sommerfeld theory, there are existence of elliptical orbits also. So, by considering Bohr's theory, we can say generally circular orbits around the nucleus. So, we quantize these circular orbits also. So, generally for the quantization, we consider principal quantum number for different circular orbits. So, for the first circular orbit from the nucleus, n is equal to 1 and it is also named as K shell. For the second circular orbit, the principal quantum number n is equal to 2 and it is also named as L. So in this way, third circular orbit n equal to 3 and it is also named as M. Fourth circular orbit n equal to 4 and it is named as N. In this way, we give principal quantum number for different orbitals. But whenever we consider elliptical orbits, so for example, for n equal to 1, that means K shell. Here, according to Sommerfeld theory, only the values available for L is only 0. That means n minus 1. The values for L equal to there are n minus 1 values from 1 to n minus 1. 1 to n minus 1. So for n equal to 1, there could be only L equal to 0. The value is only 0. And here, that means if it is the nucleus, for n equal to 1, the L value for the same circular orbit L equal to 0. If L equal to 0 means the orbit is circle itself. But if we consider elliptical orbit, for example, n equal to 2, second orbit, n equal to 2. So we can see L values L equal to 0 and 1. There are two L values. One for this L equal to 0, and there is an existence of elliptical orbit for which L equal to 1. So here for this elliptical orbit, n is equal to 2 and L equal to 1. So for the principal quantum number n equal to 2, there are two states. We can say states. For example, if you see n equal to 3, third circular orbit, the principal quantum number is 3. That means here for this circular orbit or for the principal quantum number n equal to 3, you can see 3 different L values. That means 0, 1, 2. That means up to n minus 1. Here n equal to 3 means up to 2. From 0 to 2. 0, 1, 2. 3 L values. That means for circular orbit L equal to 0, and there could be one more If it is the nucleus, it must be like this. L equal to 1, and there should be one more elliptical orbit, L equal to 2. So it seems a little complicated, but the internal structure of an atom would be like this, according to the theory of Sommerfeld. So here again, if we consider the energy of electron in any orbit, either it is circular orbit, that means L equal to 0, if the value is L equal to 1, this orbit, or this orbit, if the electron is revolving any orbit, the circular orbit n equal to 2, here also L equal to 1, n equal to 2. This orbit, elliptical orbit, L value is 2 and n value is also 2. N value does not change. L value changes according to the eccentricity of the ellipse. So the shape also changes. As the shape changes, the L value changes. So L is the orbital angular quantum number. N is the principal quantum number. But if you see, if you calculate the energy of electron in any orbit, even the circular orbit, or the orbit having the L value 1, or the orbit having L value 2, the energy of electron is the same. It is observed to be same for the electron revolving in all those three orbits. So Sommerfeld failed to so Sommerfeld failed to describe about the splitting of spectral lines after considering the elliptical orbits also. Even though after considering relativistic motion of electron in elliptical orbits, he could explain only spectral lines for hydrogen atom only. He failed to explain spectral lines for higher electron atoms, higher number electron atoms, even after considering the relativistic motion of electron in elliptical orbits. So that is due to the spectral lines splitting is due to existence of elliptical orbit and also spinning of electron. So these elliptical orbits again having different directions. Orientation of elliptical orbit is considered in vector atom model. That is one important aspect for the splitting of spectral lines for different atoms. So once again here, even considering elliptical orbits, and again these elliptical orbits, if we consider uh, nucleus, elliptical orbit, even elliptical orbit can orient in different directions, maybe like this, or maybe orient in this direction. So the same shape of elliptical orbit can be in different orientations. So we will see all these things in the next slide also. So having all these elliptical orbits, same energy values will not bring separator or splitting of spectral lines. So there should be inclusion of spinning of electron that brings the spectral line splitting. So we will discuss how these splitting occurs, splitting of energy levels or spectral lines occurs in the next slides. So here, whenever we consider an atom here at this position in the presence of magnetic field B bar, which is in the direction of z axis, this is the z axis. So the magnetic field is present in the z axis and electron is in this position. And this is the position of atom. So whenever an electron is revolving around the nucleus in a particular orbit like this is the orbital of electron motion. So the orbital magnetic momentum vector, the motion of electron can be represented by orbital magnetic orbital angular momentum vector L bar. This is in the direction perpendicular to the plane of the orbital. So this is the plane of the orbital. This is the plane of the orbital. So the direction of orbital uh, angular momentum vector is perpendicular to the direction of plane of the orbital of the electron. So this is the perpendicular direction to the plane of the electron orbit. So the angular momentum, orbital angular momentum is in this direction. That is represented by orbital angular momentum vector L bar. So the magnitude of orbital angular momentum is given by the length of this vector, and it makes an angle theta with the applied magnetic field. That is theta here. We are assuming theta, angle between orbital angular momentum vector L bar and applied magnetic field B bar. And here LZ is the orbital angular momentum component along the z direction or field direction. So the angle between theta can also be said as angle between LZ and L bar. Okay, so LZ here is the scalar, whereas L bar, orbital angular momentum L bar, is the vector. Okay, so the component of orbital angular momentum in the direction B bar or magnetic field is given by Lz equal to L cos theta, as it is the component along the field direction. It can be written as Lz equal to L cos theta, as theta is the angle between these two components, Lz and L bar. So here Lz equal to L bar magnitude. This is the magnitude of L bar and cos theta. And cos theta can be simplified as Lz by L. These two are magnitudes, L bar. But quantum mechanically, these two components, orbital angular momentum L bar and along the z direction, component of orbital angular momentum along the direction of field, can be taken as, for example, L, the magnitude of orbital angular momentum can be taken according to quantum mechanics. L into L plus 1 H cross or H by 2 pi. Let this equation number 1. And the z component, uh, the orbital angular momentum component along the field direction is Lz, that is given by ml h cross or ml h by 2 pi, whereas L is the orbital angular quantum number, and ml is the orbital magnetic quantum number. Okay, so if we substitute the values of magnitudes of L and Lz in this equation, we will get the angle between L and Lz. So let us see, let us try to find the angle cos theta, or this theta can be written as L comma Lz. That means cos of L comma Lz is equal to Lz by L. Lz by L. So ml h by 2 pi by square root of L into L plus 1 h by 2 pi. So here h by 2 pi, these two can be cancelled here. So we are getting ml by square root of L into L plus 1. So the angle between orbital angular momentum vector L bar and component of L bar in magnetic field can be determined by orbital magnetic quantum number and orbital angular quantum number. Okay, so let us see how to find the angle between L and Lz with an example. For example, here let us see L equal to 2. If L equal to 2 for a particular electron, so it can have values ml there could be 2l plus 1 ml values. The number of, for a given L value, the number of ml values will be equal to 2l plus 1. So in this case, in our example, L is 2, that means there could be 2 into 2 plus 1, that means 5 ml values. 5 ml values, and the ml values are given as -2, -1, 0, 1, 2. So the ml values are for any given L value, ml values are -L, -L plus 1, -L plus 2, etc. up to 0, 1, 2, and up to plus L. Okay, so for L equal to 2, we are getting ml values -2, -1, 0, 1, 2. So that means the electron is orbiting around a particular elliptical orbit with a L value 2 that can have 5 orientations. That particular orbit can have 5 orientations, 5 different orientations. For example, this is the nucleus, and if the orbit having L value 2, so it can have 5 different orientations with the same L value. Same L value. So L is 2 here, but with the same L value, this is also 2. Here it is also 2, 1, 2, 3, 4, like this. There should be 5 different orientations. These orientations are indicated by ML values. So this quantum number is called orbital magnetic quantum number. That depends on the or that is represented in the direction of with the reference with the direction of magnetic field. Okay, so let us see how these directions are represented or how these quantum numbers are given. In general, if we want to represent the state of electron, we need 4 quantum numbers as discussed in the earlier lecture. Those 4 quantum numbers are principal quantum number, orbital quantum number, and orbital magnetic quantum number, spin quantum number, spin magnetic quantum number. So these 4 quantum numbers are required to represent the state of the electron in an atom. Okay, so how we represent the orientation? Along with even we already said that even the electron orbit is having different orientations, the energy of all these electron in all these orbits are same. There are existence of several orientations for electron orbit, even though the energy of all these electron in all these electron orbits are same. So later, the main aspect of the vector atom model is spinning of the electron. So whenever we include this SS, we will see. We will consider spinning of the electron later. First, we will see how these uh, orientations will be in the space. So the with respect to ML values. So we already observing that there are 5 different orientations. 5 different orientations. So for example, for L equal to 2, there are orientations like this. Let us find the magnitudes of L bar and Lz also in order to calculate the orbital angular momentum, magnitude of orbital angular momentum, and orbital angular momentum component in the z direction. We know that L is given by the magnitude of L is given by square root of L into L plus 1 h by 2 pi, and Lz equal to ml by ml into h by 2 pi. So the orbital magnetic momentum component will be depending on the L value, orbital quantum number, orbital angular quantum number. So here L value is 2, L value is 2. So the orbital, the magnitude of orbital angular quantum vector is equal to square root of 2 into 2 plus 1 h by 2 pi. That means we can have 2 into 3, 6h by 2 pi. So the magnitude of orbital angular momentum vector is 6h by 2 pi, or 6h cross. And if you see Lz value, component of orbital angular momentum, and the direction of field is given by ml value. So ml can have values like this. So ml h cross. So let us see. L value is 6h cross, or 6h by 2 pi. Lz equal to ml h by 2 pi. So ml values can be having -2, -1, 0, 1, 2. So minus 2h by 2 pi, minus 1h by 2 pi, 0 h by 2 pi, minus h by 2 pi. So the jet component of orbital angular momentum having different directions. These 5 different directions. Okay. So these different orientations of electron orbit can be represented in this diagram. Here, this is the direction of electron orbit for which ml equal to 0. ml value here is 0. That means here the component, the length of the component of L bar in the direction of magnetic field is 0. Is 0. And again here, the electron orbit maybe like this. If it is orbiting like this, the ml value is 1, and the length of the Lz is h by 2 pi. And here for ml equal to 2, the length of the jet component of a orbital angular momentum is 2h by 2 pi. This is the negative values, minus for ml equal to -1, minus h by 2 pi, minus ml equal to -2, minus 2h by 2 pi. So these are the 5 different orientations of electron orbit around the nucleus. So let us calculate the angle between L and Lz. So the angle is given by cos theta, or may represent this as L comma Lz, L bar comma Lz, that is given by magnitude of, we can see here the earlier expressions, earlier derivation, cos theta is given by Lz by L. So Lz by L. So these two should be magnitudes. That means length of the Lz and length of the vector L bar. So Lz is given by mlh cross. We already calculated these values also, this expression also, that is given by ml by square root of L into L plus 1. as we already calculated the cos of angle between L and LZ as ml by square root of L into L plus 1. So now let us see the value of L is 6h cross for L equal to 2. So for this particular electron, this value is constant. And again, ml as ml values are changing from -2 to 2 in the steps of integer, and LZ values also changes. Those values are given here. So the angle, let us write here. The angles, different orientations. That means the angle between L and LZ can be given by ml. ml means here is ml values are -2, -1, 0, 1, 2. So -2 by square root 6 and -1 by square root 6, 0, 1 by square root 6, 2 by square root 6. If we calculate the angle between L and LZ, that means cos inverse of all these values individually, we are getting, that means cos inverse of -2 by root 6 or cos 0, all these values. So this will give 135 degrees cos inverse of -2 by root 6. Cos inverse of -1 by root 6 will be 114 degrees. Cos 0 is 90 degrees. Cos inverse of 1 by root 6 is 66 degrees. And then cos inverse of 2 by root 6 is 35 degrees. 35 degrees. Okay, so that's why we are seeing 90 degree here for cos 0 value. For ml equal to 0, we are seeing the orbital angular momentum vector 90 degrees with magnetic field direction. And for ml equal to 1, means this value, ml equal to 1 here. So for this, the angular difference between L and LZ or L and B bar is no, this is 35 degrees. You will get 35 degrees here. Here 66 degrees. Okay. So for ml equal to 1, we are getting 35. These are same only. 66 and 35. These two are correct only. So for ml equal to 1, we are seeing the angular difference theta, the angle between L and LZ or L and magnetic field is 66 degrees. And for ml equal to 2, the theta is 35 degrees. These two are correct only. For ml equal to -1, we will see 114 degrees between L and B bar, or L and LZ. For ml equal to -2, we will see angle 135 degrees. So these are the different possible orientations of electron orbit. So the electron orbit number is quantized. That means there could be no other possible orientations. Only these orientations are possible for L equal to 2. There could be no other possible orientations except these orientations for the electron. So these are the different orientations. Those are quantized. That means quantized. So this is only called space quantization. This is only called space quantization. And whenever we already said that even though they have different orientations for the electron orbit, all the electrons or electrons in all these orientations will be having same energy values. There is no change in the energy of electron, even orientation changes. Orientation of the electron orbit changes. So we have again spinning of electron. So the electron can have two different directions of spin. So those are represented by, again, in the similar manner as in the way we took the directions of orbital angular momentum. Spin also can have two values in general. So it is also represented by spin quantum number, spin quantum number. So it is also represented by S. So S can have two values. Generally, S is always 1 by 2. It can have 1 by 2. And as like, it is as like L, similar to L. As like L is having ML, orbital magnetic quantum number. In the presence of magnetic field, electron spin also can have uh, spin magnetic quantum number, MS. So for S equal to 1 by 2, MS can have two values, plus or minus S value. That means plus or minus 1 by 2. For a single electron atom, the electron can have two spin magnetic quantum numbers, plus 1 by 2 or minus 1 by 2. So that again we should discuss about the quantization. Here it is the spin quantization. Spin uh, spin is also can be represented. The length of the spin uh, length of the spin momentum. Spin momentum can be represented by uh, as like L bar. Here also S can be represented by square root of S into S plus 1 h cross or h by 2 pi, and the length of S component in the magnetic field direction, that means that is Sz is also given by ms into h cross or h by 2 pi, h by 2 pi. So whenever as the s values, uh, the available s values are that means ms values are 2, there are two different ms values. The electron in along with the orbital angular momentum can have spin quantum number. Whenever by adding the spin quantum numbers, we can have as it is plus of and minus of we, the energy values of electron even having same values with the different orientations of electron orbit due to the existence of plus of and minus of spin, the energy values differences having two different values. A slight change in the total energy will be occurs. So these change of electron energy slightly can cause for the splitting of spectral lines. So there should be two spectral lines. One spectral line will be appearing as two separate spectral lines. So again, how we should add in general these two orbital angular momentum in general. If we consider a single electron atom, that electron can have orbital angular momentum maybe in this direction. This is the L bar is the vector representing the orbital angular momentum in this direction. So this is the length of the orbital angular momentum. This is the length of the orbital angular momentum in this direction, and this is the spin momentum, spin momentum of the electron, which is in this direction. This represents the length of the or magnitude of the spin momentum. So, in general, spin momentum will be very less compared to the orbital angular momentum. So, but however, the spin momentum also raises the total momentum of the electron. So, we need to add up these two momenta. So, whenever adding these two vector momenta, we need to utilize the vector analysis. So, in the vector addition of these two vectors, will take a total angular momentum as j bar. So, this is the L vector and this is the spin vector, spin angular momentum vector. This is the orbital angular momentum vector. So, whenever adding up these two vectors, you will get a different vector j bar that is called total angular momentum vector. So it is given by j bar equal to L bar plus S bar, L bar plus S bar. As like in the case of orbital angular momentum vector, j bar momentum vector is also given by, according to quantum mechanical description, the length of the j bar can also given by square root of j into j plus 1 h cross or h by 2 pi, and the length of total angular momentum component in the direction of magnetic field is given by Jz, that is also given by Mj into h cross or h by 2 pi. The Mj values are given from minus j to minus j and minus j plus 1, minus j plus 2, so on up to 0 and 1, 2 up to plus j, plus j. These are all the values that Mj can have. And again, from this equation, from vector summation, if we calculate the, or if we square up the vector j bar, so we will get the magnitude j square, that is equal to L plus S whole square. So we will get here magnitude j square equal to L square plus S square plus 2 into L bar S bar generally, and it is also can be written as L into S into cos theta, that is angle between L and S bar. So if we want to find out the angle between these two vectors, orbital angular momentum vector and spin angular momentum vector, so if we try to find out cos of this value, we'll see all these are magnitudes. So if we try to calculate cos of angle between L bar and S bar is equal to j square minus L square minus S square by, after taking these two terms to the left side, we can take these two terms under the denominator 2 into L bar into S bar, or magnitude of L and S maybe. So we are taking magnitudes. So we already know that the magnitude of J bar is given this expression. L bar is also the same way. L bar is also given square root of L into L plus 1 into h by 2 pi. S is also given by the expression S into S plus 1 h by 2 pi. So we can easily calculate the angle between orbital angular momentum vector and spin angular momentum vector. So we will see how to calculate the angle between L and J, LZ and L and S with examples in the next class. Here we will see, as we are having L bar in this particular direction, S bar in this direction, these two will give or add up to give a total angular momentum J bar. As we seen the orientation of L bar with reference to the magnetic field, let us see the orientation of J bar with reference to the magnetic field also. So for this here, so this is the L bar vector. As we seen in the starting slides, this makes some angle theta as we represented in that slide. The angle between L and LZ, that is the component of orbital angular momentum vector with reference to the magnetic field. So this is the LZ vector, LZ scalar component of L. So that makes theta angle with L. And again here after considering the spinning of electron, this is the vector representing spin angular momentum. So it makes some angle like this. So after adding the orbital angular momentum and spin angular momentum of particular electron in an atom, it gives up a total angular momentum j bar in this direction. So this is the precision of j bar with reference to magnetic field b bar. So this also makes some angle with reference to magnetic field. In general, we discuss the orientation of orbital angular momentum the precision of orbital angular momentum with reference to the magnetic field. That is also called Larmor precision. Larmor precision. So the orientations, the precisions precision of electron orbits about magnetic field direction. Magnetic field direction is called Larmor precision. Is called Larmor precision. So whenever we add up orbital angular momentum and spin angular momentum, it gives up total angular momentum. So finally, we need to consider the orientation of total angular momentum precision about the magnetic field direction. So it is also quantized. The total angular momentum is also quantized. So finally, we can say that the orbital angular momentum L bar, the spin angular momentum S bar, and J bar, total angular momentum vector J bar. All these are quantized. And again, having a slight difference due to the addition of spin angular momentum, there should be slight difference in the that means slight different energies are available for the different orientations of the electron in different electron orbits. So that means there are different quantum states. So they are represented by N, L, Ml, and Ms. Here, instead of these two terms, we can represent in the different notation also. So we will see all those representations of quantum states in different notation, that is also called spectroscopic terms. We will see how to represent different quantum states with different spectroscopic terms, that is called spectroscopic terms, in the next lecture. So these are the references given here. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.